Well, friends, the moment we've been waiting for, we get to talk about transversals and parallel lines. And we get to take a look at that diagram that you are so familiar with from back in the day, how you've got two parallel lines, L and L prime, and you have some third line that comes through. It's called T. It's a transversal, and that transversal intersects both of the parallel lines. This is the picture you're familiar with from way long time ago. When we talk about two lines being cut by a transversal, we talk about two kinds of angles. We talk about interior angles, meaning that the angle is so-called between the two parallel lines. And we talk about exterior angles, where the angle is sort of outside of the zone between the two parallel lines. So we refer to this angle and that one as alternate interior angles because one of them is on one side of the transversal and the other is on the other side of the transversal, but they're both between the parallel lines. Similarly, the red angles are alternate interior angles. This one's on the so-called left side of the transversal. This is on the so-called right side of it, and that's just really rough language. There's no left, there's no right of the transversal, but they are both between the parallel lines. So that's the vocabulary that you need so that I can talk about the alternate interior angles theorem, sometimes abbreviated AIA. The alternate interior angles theorem says that if L and L prime are two lines cut by a transversal, such that the alternate interior angles are congruent, then L is parallel to L prime. That's the idea. Oh, by the way, for all my latexing friends, L is \ELL, parallel is \parallel for all my latexing friends. So here's the idea. We can do this real easy. I'll just get rid of these things. Let's suppose you have two lines cut by a transversal and the alternate interior angles are congruent. How do we show that the lines are parallel? Well, how do you show that two lines never meet? You pretend that they do and show that something goes wrong. So let's pretend they do. Let's pretend that these two lines meet somewhere down here. Then we would have a triangle this point, that point, that point. There's nothing wrong with having triangles, right? Except that this angle right here is an exterior angle to that triangle, this point, that point over here. And this exterior angle would be congruent to a remote interior angle, wouldn't it? And that violates the exterior angle theorem. And so it is not possible for these two lines to meet somewhere out here. And so these two lines cannot meet. Similarly, they cannot meet out this way for the same exact reason. So if the lines can't meet on this side of the transversal, the lines can't meet on that side of the transversal, then the lines can't meet at all. L is parallel to L prime. Time now for a warning. Warning, 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 warning. The logic here works only one way. If the lines are cut by a transversal such that the alternate interior angles are congruent, then the lines are parallel. The logic does not say if the lines are parallel, then the alternate interior angles are congruent. Does not follow. Does not follow. Does not follow. The logic goes one way. If the alternate interior angles are congruent, then the lines are parallel. So now why does that matter? Why do I care about that? Well, I care about that because we have a huge corollary coming off of this. This is a huge corollary. If if L is a line, and P is a point not on L, then there exists a line M such that P is on M and M is parallel to L. This is where the elliptic parallel postulate drops off the map for us, because this is where we prove that in neutral geometry, parallels must exist. And this is actually really easy to prove. That's a line. That's a point not on the line. You and I both know that we can construct the perpendicular through P to L. We know that that perpendicular is unique. But then we can, second verse, same as the first, look at the line through P and construct the perpendicular to that line. We construct the perpendicular to that perpendicular through P. We have proven that we can do that and that that perpendicular is unique. Now this line M has alternate interior angles that are, this line M and this line L are intersected by this transversal T, and the alternate interior angles are congruent. And because, I should probably use colors to accentuate that. Because the alternate interior angles are congruent, the lines are parallel. This is sometimes called the double perpendicular construction. It's named after the very famous mathematician double perpendicular. It's a double perpendicular construction, and it is super important because it means that the elliptic parallel postulate fails in neutral geometry. Okay? Okay. Great. So that's important. Glad you're here to see it. I'm done.